Let me first introduce Peter for those of you that don't know him. He's been around at the TUE and DIFFA for a long time. I've known Peter ever since he did his master's project at Princeton, working on a liquid metal diverter design for NSTX-U, which I think is a design that they're still quite happy with and planning at some point in the future to perhaps install. But after that, Peter did such a good job that we persuaded him to do a PhD in Eindhoven, which built on this. And you will probably see something about this in the presentation. He started that in 2015, and afterwards in 2019 he secured a Eurofusion engineering grant, which again built on all the successful and great work that he did during his PhD. So Peter is somebody, I would say, with a huge amount of ingenuity and energy and enthusiasm, and he was also, I should mention, started his and co-founded his own startup called ESOX. And this is something I don't fully understand how it works, but it's more or less is for collective bargaining for sustainable and green energy solutions for your energy needs. It sounds very cool and the sort of thing that we need to move into a green society. And so without further ado, I hand the floor to Peter for this should be very interesting colloquium. The floor is yours, Peter.
Yes, thank you. Thank you a lot, Tom, for this great introduction. I hope I can live up to it a bit. Yeah, so thank you all for joining. Indeed, the point was also to promote this competition a bit, but also actually the point would be that I hope to provide you in return with a very interesting talk that I hope you really will enjoy. So let's just dive right in. And I want to take a look at this movie to show you that there is a huge challenge in fusion, which is developing the heat shields, because these are living in a rather violent environment, I would say, as you can see here. And of course, this is only an experiment done in Magnum PSI, but the reality will be many times more severe conditions, actually, or at least a few times. And as you can see here in Magnum, already the cameras have a hard time keeping up. Imagine what the sample has to go through that is directly exposed to this heat load. So let's take a look first at why these heat shields are so important. And then afterwards, we'll dive into the real work. So the story starts with fusion, of course. This is a nuclear fusion research. And we are doing this because it is a sustainable energy source. And as you all know, there are some advantages. There is, the same type of nuclear reactions as in the sun, which means that there are very little to non-nuclear waste products from this reaction. It is inherently safe. There are no, risks at runaways or meltdowns, this kind of thing. There is abundant fuel for 1,000 years or so. And finally, what I find also very important is that it's quite compact. And we do not have unlimited land. So this is actually an important point. Now, currently is a very exciting time for fusion. Actually, ITER, the first reactor to produce net energy, is being built as we speak and should produce interesting results in the coming years. But that being said, it will take still many more years to really deploy a large amount of fusion reactors. So if we look at the energy transition on the relatively short term, which I've just put here as about 50 years from now, we are trying to prevent catastrophic climate change, and fusion will have a very, very limited role in that. But on the long term, we do have to work towards a sustainable energy system that can last for a really long term. And in that energy system, I do believe that fusion will have an important role to play. So that is why fusion is important. What about these heat shields? Now, this is also, of course, very familiar if you are already a fusion expert. But in the reactor, we have a plasma in which the fusion reactions take place. But the plasma and the power that is being generated flow outside along a magnetic field. And you can see the path indicated by the lines towards the wall of the reactor, and in particular toward a set of shields at the bottom, which is called the diverter. And in the diverter, the impact of this plasma and this power is the biggest. So easily the diverter can melt. And moreover, if you lose control of the plasma and it becomes destabilized, in about a millisecond or so, you can destroy your entire diverter, which means there is $1 billion investment down the drain. And so that means if we cannot build a diverter that cannot survive a disruption, then nobody's going to build a fusion reactor. Yeah. And it will, in fact, be very impractical to operate it because there is a chance that such a disruption occurs. Now, interestingly, the opposite is also true. If you could make a better diverter, what you actually do is you remove one of the constraints on the reactor design, and you could explore new ways to scale it. So, for example, you can make it more compact and therefore cheaper, and therefore an easier investment. So, a better diverter might definitely make for a better reactor, which is very nice. And so this is where my job actually lies. So my job is to do R&D, research and development, to create this better diverter, and we're going to do that with liquid metals. So the question is, are liquid metal diverters the solution for fusion, for the future of fusion? And I want to talk to you about the 3 steps that I took. And the first one is, let's design actually a very small experimental type of diverter that allows us to do experiments and to gain insight into behavior and to the performance that a liquid metal diverter might provide. So let's take a look at the principle to start with, so you understand. There are 2 general principles which we very much like about liquid metal diverters, which is that first, they are self-healing. And second, we think they can withstand incredibly high heat loads because of something called vapor shielding. And to understand exactly why that is the case, let's take a look first at a conventional solid heat shield. So what you see here is a version of a tungsten diverter. And actually in the picture you see a tungsten armor layer in a sort of grayish color on top of a copper channel through which water will flow. And this is a bit of a special mock-up, but because usually the tungsten goes all the way around. And these are, state-of-the-art solutions. There actually goes a lot of engineering into manufacturing the tungsten, into joining the tungsten to the pipes, all these things. It is really state-of-the-art. But nevertheless, there is a sort of inherent limitation. And because the problem is that the plasma will erode the tungsten. And so to have a long lifetime, you want to start out with a nice thick block, and this will get thinner over time. But okay, if you start out with a thick block, you will have some lifetime. But at the same time, you want to keep the block from melting. And well, to keep the surface cool, you want to make the block thin. That is how thermal conduction works. A thicker block will get hotter on the top. So you want to start out with a nice thin block from this perspective, not a thick block. And this is an inherent conflict of interest that you can only go so far in compromising. For a liquid metal diverter, you can then immediately see why this might be a good idea. So the plasma heat flux again erodes some liquid metal, but that's fine because you can have a liquid metal flow and there can be replenishment. And so we have point 1, self-healing. And the evaporated metal goes actually into what we call a vapor cloud. But this vapor cloud also acts as a sort of shield, hence the term vapor shielding. So power is dissipated by this cloud because the cloud heats up, the particles are lost to elsewhere, or maybe they radiate. And this, we think, or thought, and now we know for sure, can be a very effective way to dissipate heat. But then there remain some practical challenges. So how would you go about keeping such a liquid in place? Because, there is gravity, there are magnetic fields and currents pulling at this liquid and wanting it to move all over the place. So keeping it in place is usually done with capillary forces. So like a sponge, the liquid is sucked up and it stays in place quite nicely. And one typical way to make these porous structures is to use meshes. So basically layers of woven metal wire. But this is not straightforward. So here you see a sample that we exposed in Magnum at the beginning of my PhD, and after a single plasma exposure, we melted through all these mesh layers, and it's a complete wreck, so to say. And then what I did is I actually made another target, and this one has a single mesh layer on the top. But in the middle of that, you can already see there is a hole. And behind that was a reservoir and some other things. But the mesh layer is damaged, and that is not ideal. And even if you have expert builders, so for example, here's a great picture that was sent to us from Compass. They installed a liquid metal limiter, which is also a plasma-facing component. This was built by a Russian team that are also absolute experts on making these components, but even there you can see there it has spectacularly failed, unfortunately. So there are big holes and the liquid metal has gone all over the place. Although it was still a very useful experiment, I should say. So how do we fix this? We came up with the following. Let's do some 3D printing. So Philips has developed for X-ray optics the capability to print tungsten. And you can do something fantastic with this. Namely, we designed a component that works a bit like an oil lamp. So there's a reservoir, there's capillary flow to the plasma-facing surface, and then that plasma-facing surface is supplied completely automatically, passively with liquid metal. And this works very practical. So you know, you take a bunch of these, you fill them in outside of your experiment, you prepare them, then you put them inside your experiment, you use them until the liquid metal is depleted, and well, afterwards you fill them again, which looks beautiful, by the way. So here's a target filled with lithium in the glove box at Differ. So this works great. And what's even better is that because we can use 3D printing, because of course, you know, there are other ways to make solid porous materials. But with 3D printing, you can really control very well the internal geometry of such a sample. So you can maximize capillary flow, and you can reduce thermal stresses due to, you know, heating, thermal expansion, bending. You can reduce those stresses to virtually negligible levels. So 3D printed tungsten is not as strong as regularly manufactured tungsten. It's only about has about half the strength, let's say, but it's absolutely irrelevant because the stresses are also irrelevant. And from that perspective, for those of you who are familiar with neutron loading, neutrons continuously degrade the materials in fusion reactors. That's a big problem. But we might wonder, actually, is that still a problem here? If the material has virtually no need for strength, does it matter if we lose a little? So that is actually very interesting. Side note here. All right, so we made a bunch of these samples. Now it's time for step 2. Let's do some research. And the question here is, this vapor shielding mechanism, can we understand how that works? And what are the limitations, actually? Is it enough to survive, for a component to survive in a real reactor? We use Magnum PSI. You have seen it already in the movie in the beginning. It is a linear plasma beam that creates conditions very similar to a tokamak, actually. We can add millisecond pulses on top of a steady state load. So you can have a steady state, you know, you can turn the plasma beam on for hours, but you can add millisecond pulses to mimic plasma instabilities on top of this. For those in the fusion field, of course, I refer to the ELMs. And then we can measure a lot of things, as you know, but today I'm going to take a look at surface temperature, a view from the lithium cloud that we can see from the side with a high-speed camera. And of course, we can example the samples afterwards. Okay. Now, the temperature is maybe the most trivial thing, but it's also, I find, the most interesting and most insightful thing. So what we see here is a striking difference if we view the temperature over time between samples that have been put in as a reference, so a 3D printed sample without any liquid metal inside, and on the other hand, samples filled with lithium. And the striking thing is that, of course, the empty samples, if you increase the power gradually until 16 megawatt per square meter, which is very significant, of course, the temperature of the samples increases. While for the lithium, this doesn't seem to be the case. The temperature is fixed. There is no change in temperature for some reason. And the reason is vapor shielding. So as I explained before, liquid metal evaporates. The liquid metal particles, they heat up, they ionize, they start radiating, they are transported elsewhere. In any case, heat is dissipated and not going to the target anymore. And in fact, we can say from this figure alone that probably up to 2/3 of the power is dissipated by vapor shielding for sure. And if you wonder how you can estimate that, think like this. So we know there is vapor shielding and on the other hand, thermal conduction. Now, thermal conduction is determined by the temperature difference between the surface and coolant. And we know that the cooling water is at 20 degrees Celsius, at least in Magnum PSI or whatever it is in another setup. And the surface temperature is locked. We find experimentally that it's always locked at 850 degrees. So that means that if this temperature difference is fixed, also the amount of power going to the coolant is fixed. And this is actually great because you can easily destroy your sample if you put too much power to the coolant. So you can imagine maybe water will heat up, especially where the plasma hits. And if it starts to boil, if you put too much heat, at some point you have boiling to such an extent that you have zero cooling anymore and your component will just fail. So this is actually a great way to try and avoid that mode of failure. And all the rest of the power has to be vapor shielded. Yeah, that is how you can determine roughly how much power you vapor shield. And then maybe a final note on the question why. Why do we have this locking at 850 degrees Celsius? And the answer here lies into the mechanics of evaporation, more or less. So evaporation is a temperature-different process, and it goes as a very strong function of temperature. So even the slightest few degrees of temperature increase will give you a very large increase in evaporated particles. And because of that, you only need a very small temperature increase to dissipate, to have a lot more vapor shielding, right? Yeah, so you always end up around this 850 degrees C, but in theory, if you put a lot more power, it should be able to exceed this temperature, right? Because you will need slightly higher temperature to evaporate more particles to handle higher heat loads. So let's take a look at some pulses. We know this works in steady state, but what happens during a pulse? And as I said, Magnum can do this quite well. And what we have done here is the most severe loading that we ever did on a sample like this, which is instabilities of 1 millisecond each applied at 100 Hertz. And if you see here, I noted in green that each of these little peaks is actually about 15 pulses that are so close together that you cannot discern them in this figure. What you can see, the lithium target in red, is that the base temperature stays more or less constant. The temperature peaks are very high, but actually we think that is because the infrared camera is picking up emission from the vapor cloud rather than the surface. So we expect this temperature rise on the surface to be much less. And there's no damage, which we also could observe afterwards. So these samples survive perfectly. Whereas the dummy target without lithium, you can see there the base temperature keeps increasing until about halfway, and then suddenly it seems to dip. And what you see there is actually melting. So there is a big melt pool of molten tungsten. The emissivity of that is lower, the infrared emissivity, and that is why the temperature seems to drop. And afterwards, you can see actually that we did make a beautiful drop of tungsten there on our target, which was, of course, unfortunately for the target, but it was a very interesting result. So what can we conclude from this? Well, I would say first, also vapor shielding still provides sufficient protection in this case. And keep in mind, the loading here is really quite severe. If you would calculate this as an average heat flux, I mean, this is with a wide margin of error, I should say, but it should be somewhere between 25 or 50 megawatt per square meter. it is on this ballpark. And keep in mind, in a fusion reactor, the steady state heat load that we aim for is about 10 megawatt per square meter. So this is well above that. Yet the target survives. But again, we should note evaporation may be significantly increased in these cases, right? Because to deal with these extremely high loads, we will get increased temperature despite the temperature locking effect to evaporate enough lithium. And in fact, now I'll show you some of these camera images. We can have fantastic measurements, really beautiful images, I think, of what happens during a pulse. So you can see from left to right and from top to bottom what's happening in chronological order. You see in steady state, we have, you see the target outline in red, and there's a white lithium cloud. That's because it's just a black and white image that is right in front of the target. And then during a pulse, suddenly we get this bright layer of light wrapped around the target. And you can see after the pulse that this layer expands rapidly. It expands really fast. So it appeared that there was, in fact, some sort of compressed high-density vapor layer, which I thought was very interesting because, in fact, you cannot evaporate an infinite amount of liquid metal because it will interfere with your fuel mixture. So there are significant limitations to what you can evaporate, and we should be careful. Even though we can withstand pulses, which is great, we should still be careful to what we should load this component to. Yeah. There are many more interesting things to say about this. For example, at 100 hertz, at some point, we started to observe shock waves. So there appeared to be a buildup of lithium density in the chamber, and you see all kinds of fascinating things, but I will not go into the full depth in this talk, where there's also a bit of a general audience. But if you're interested, please ask me afterwards. So now that we have a bit better understanding of what we can do with vapor shielding, let's do the final step. Let's design an improved diverter and see if this can live up to our expectations. And I'll just drop in right with the design. Here's what it looks like. It's, again, a water-cooled design. That's a very proven technology, so we're going to use it. There is a square pipe that is round on the inside through which the water is flowing. We have picked 180 degrees Celsius to keep our metal liquid on top, 150 bars to avoid boiling. And then on top, you see on the top, there is this 3D printed texture. That is where the liquid metal is going to be loaded in. And we can play a bit with the thickness of that layer. So how does it look in a full component? Actually, we have to build a vertical wall. So it has to stand straight up. It has to be about 1 meter high, actually 70 centimeters. So that's why it has this orientation. This is the 3D printed texture. It sits on top of these cooling pipes that are curved towards the back, as you can see. And the whole thing is actually placed inside a bath. So the idea is to get a good cover over the whole surface to get this reliable. We inject liquid tin from the top, and gravity is just slowly going to drive that to the bottom. Very, very, very slowly. Actually, because there is a little bit of viscous drag, but also there is magnetic drag, which is very significant because of the high magnetic field. And then there is the coolant going through the pipes. That is roughly the layout. All right, so we've set these parameters, and now we can assess, did we do our job? That is the question. So let's assess the performance for 2 thicknesses. I will start with 2 millimeters and then increase to a 3 millimeter thick printed layer. So in the steady state, remember, in steady state, actually, there's no vapor shielding allowed because if we have too much evaporation, we contaminate the plasma. We are required to dissipate about 10 megawatt per square meter. And it seems in this case we can do it. So while keeping below our evaporation limit, which is in fact the surface temperature limit, we can dissipate about 26 megawatt per square meter. If you put a safety margin on that, there is still 18 left. So this is very good. In off-normal operation, so let's say we lose the control of the plasma for a little bit, we could expect the heat load to go up significantly to about 80 megawatt per square meter. And this is too much still. I would predict we can dissipate around 40 megawatt per square meter. That is much better than the current state of the art, but still it's not enough. And then finally, there are the disruptions. Disruptions, just to put into perspective, are still about 100 times more severe than the pulses that we tested in Magnum. So this is a really, really difficult thing to assess. Based on our modeling and the experimental results so far, we think it should be plausible. And that is already a huge improvement. But just to be sure, we have filled these 3D printed samples of ours with tin, and we have sent them to Ukraine. So in the coming months, they will be tested, and this will be a very exciting result, actually. So what happens if we go to 3 millimeter? The surface is thicker, it will heat up more easily. That's why in steady state we can reduce, we have to reduce the maximum load to about 18 megawatt per square meter. In off-normal operation now, actually, the nice thing is, because the surface is a bit hotter and further removed from the pipe, from the cooling water, actually now vapor shielding allows us to deal with this 80 megawatt per square meter. So this is fantastic. I should say also there is some uncertainty here, so that's why I've just put more than 80 megawatt per square meter instead of an actual number, because you need very good estimates of the actual energy dissipated per evaporated particle, this kind of thing. And for disruptions, actually there's no difference, because for disruptions only the top tenths of a millimeter of the CPS play a role, because the pulse is so incredibly short that the heat doesn't really penetrate much further. All right, so in any case, I would say this could definitely be an improvement. That's what this concept could be. And of course, to prove that, we should make a mock-up. We should test this thing. That's what I'm doing right now. So here you can see the mock-up under construction. There's a water inlet, a water outlet, a liquid metal outlet. There will be a liquid metal, separate liquid metal inlet. That's why it's not in the picture. And then in the middle, you can see three pipes. They are square on the outside. And that is where the CPS will be printed on top of. So that's roughly how it's going to look like. And the reason that we put it in steel is just that we have to demonstrate, the concept first, also with the flowing liquid metal. And the next step will be to make it out of the really high performance heat sink materials, the fancy copper alloys. And then finally, I wanted to end with this fantastic picture of the CPS, of the 3D printed tungsten, which is being made with Philips and with Dunlay. They did this test print on a steel slab, and the real texture is being printed as we speak on the actual mock-up. Yeah. All right. That brings us to the conclusion. So, what have we seen? We have seen that we can enable experiments. This is very important because now we can start to learn. We have learned about vapor shielding, and we have much better insights into how that works, at what temperatures temperature locking occurs, and this information we have used to develop a concept and estimate if that could be an improvement. So my answer to the question, if this is a good idea, would be yes. This is definitely a good idea. This definitely brings us closer to a viable fusion reactor. And that is my answer. So thanks for your attention. And of course, I have to promote the competition again. I really hope you enjoyed the talk and that I earned your vote. So please ask any question that you want.
Great, thanks a lot, Peter. Very interesting talk, very clear. Happy to see that there's also a bunch of questions already. I'm going to start with Hans van Eyck, just from the list that I have right here. So I'm sorry if I didn't make it in the right order, but I think Hans is first. So Hans, go ahead.
I think MJ was first, but I'll go ahead. Thanks, Peter, for this nice talk. I was wondering a little bit about the mock-up. So,
yes.
And then the flow speed of the liquid metal. So,
Right.
Can you tell a little bit more how did you determine which flow speed you need, and is it engineered for this flow speed, or you do not know?
No, so actually, yes, so I can tell you about this. So there are actually two things that you need to take care about when you are designing the CPS, and flow speed is actually not number one. What you want to take care of first is flow stability. So you have to design the geometry such that the liquid can flow through smoothly without bulging out at any point. So we tested this actually with just a water flow experiment. So we printed a bunch of plastic geometries, actually with a student, Joep, he did fantastic work on this. And that is why we selected the geometry that we have. And actually the geometry is just a really rectangular array, let's say, of these little tree-type structures. So I'll show you again. And so the channels in between these that go through this array are pointed perfectly vertical. And there you have very smooth flow, and the space in between that appears to just get filled up with capillary forces. And that's the most important thing. And then for the flow speed, of course, the flow speed should be sufficient, more than sufficient, to compensate for the evaporation that you expect. But it turns out that the evaporation rate, which of course should be very low, is indeed very low. And so, and especially the fact that we are flowing a liquid and not a gas or a plasma makes it you need a really low flow speed. So we are talking about something like 10 to the, like, let's say 0.1 millimeter per second. This order of magnitude flow speed, it's really, really low. Yeah. And of course, if you increase the field, this goes down even faster, yeah, because it goes quadratically. The magnetic drag goes quadratically with the field. Yeah.
Okay, thanks.
Okay, so I think if I understand the way the hands work in teams, I should come to Jos Scholte next, and then I'll come to MJ.
Okay, thank you so much, Peter, for your presentation. I had a question because now you've only made a mock-up. And do you know how you can go towards a larger scale for the full fusion device? Because if you would want to print it as one part, you would need a very large 3D printer. And if you're going to make it from smaller parts, do you know how you can connect it? And if you have problems where the two parts connect, so that you have not a sufficient lithium flow in this part.
Yeah, that's a great question, I think. So the reason we're doing a mock-up now is just because you want to start small, right? You want to do a small test before you invest a lot of money into a big test. That being said, though, I think the challenges that you mentioned are the right ones. I think it would be a bad idea to connect different pieces together because, you know, maybe for the 3D printed structure, that's fine, but these cooling pipes are really under a lot of stress and they really have to be leak tight. So you don't want to do that. So it would be good if we make that in one piece, develop bigger printers, which I think I don't see any technological obstacle to do that except for cost, which is in fact not a technological obstacle. And then we should print on that. There is one challenge with printing, though, also a very technical, practical challenge, is that currently these printers work with a powder bed. So there is a flat bed of powder, and you pull the laser across that, and then you swipe over a fresh layer of powder. But this bed has to be perfectly flat. But the diverter pipes may not be perfectly flat, and in fact, right, because they are in assembly, maybe the tolerances are just not good enough. So it would be great if we can think of a way to fix that. And actually, the reason that here in the mock-up these three pipes are built from one block is to create that required flatness. That is the one reason that we do this. But this will be an interesting challenge for the future, yeah. But I'm sure we can do that. There are plenty of printing schemes also with powder jets instead of beds, and well, you can get creative, yeah. But that's definitely the next stage. Yeah.
Okay, thank you very much. I have another question, if I'm allowed.
If you can make it a short one, Jos, because there's a lot of other people who want to ask questions.
Okay, I will make it short. So you have a high heat pulse on your diverter, but only a constant amount of heat flux is going towards your cooling. So you also have a large heat flux which goes towards your first wall. Do you think that gives a problem on the first wall, this additional heat flux due to your instabilities?
Yeah, that's a good question. I think not actually, because so the problem with cooling is usually not the total amount of heat, but it's the heat flux density, the amount of watts per square meter. And by radiating or somehow transporting to the first wall, which has a 1,000 times bigger surface area, you spread that out. And I think that is definitely one way to go with this. Yeah. Although I'm not an expert on the first wall and the constraints playing a role there, so I should note that. But I do think it's a good approach. Yeah.
Okay. So thanks, Jos. I will come now to MJ.
All right. Yeah. Thank you very much. That was a really well presented seminar.
Thanks.
I will say I had to miss 2 or 3 minutes in the middle of it. So if what I'm going to ask has already been answered in the talk, I do apologize. Right. So in a standard diverter or a standard wall per se, you have a constant neutron flux. The neutron flux damages the tungsten, which creates voids, vacancy clusters, and so forth. Now, when you slab liquid metal on top of that, conceivably, those voids or vacancy clusters could fill up with the liquid metal, which could do potentially one of two things, which could influence the flow mechanics, or it could impact surface chemistry. I do not know offhand with what I would expect really whether that would be an issue, but I do wonder whether there is any plan to repeat those experiments you did with the damaged tungsten samples, or damaged tungsten floor, basically.
Yeah, I see what you mean. So a neutron irradiated.
Well, neutron irradiated will be difficult, but you could, for instance, do tungsten self-damaged.
Yes, yeah,
samples.
something, a simulation of that. Yeah, great question. Thanks. Yeah, so in my mind, this indeed is a very open topic. So we have only a hypothesis. I would say there can be some pros and some cons, let's say, right? So the issue that you mentioned, that there could be pores in which the liquid metal could go, and influence maybe let's say the flow dynamics for the worse. That could be bad, but it could also be great, because now you don't have any open voids that reduce your thermal conductivity. And the same thing you could say about helium production, for example, right? There might be helium production, which leads to swelling and whatnot. But if this 3D printed tungsten is already some kind of micro porosity to begin with, so I'm talking about really the printed bulk, not the intentional porosity that we print in it, but really the porosity in the bulk there, which is also there. You might use that actually to your advantage. Maybe this is fine enough for helium bubbles to escape. I'm not sure actually, but that is a thought I would have.
It would also, though, potentially pose a problem that if tritium were bred in a lithium liquid, then that would then more easily go into the tungsten, and then you would have retention.
Yeah, that might be an issue. That's a good one. I hadn't thought of that. I should say I can add to that the European demo team, which is trying to design a more conservative design that will definitely work, is very against use of lithium, because of very good reasons. That not only do you have a tiny bit of breeding, because of course it's still a very thin layer with almost no neutron absorption or stopping power, you will have a lot of tritium absorption simply from the plasma, because lithium and hydrogen isotopes really like each other. So you can absorb the entire fuel, your tritium reserve in no time, and we know how much effort it takes to breed that. So that's not something you want to do. Yeah.
All right. Yeah. Thanks. And you might want to talk to Beata about some of the details because she's an expert on these damage.
Yeah, thanks. Maybe it's a good idea to set up a project on this. Maybe the time has come to dive into this issue. That's yeah. Thanks for the suggestion.
Sure. Thanks.
Great. Then I will come to Mariam Smithberg, please.
Yeah, I was just a little bit curious about how these disruption testing in Ukraine will actually happen.
Right. Yeah. Okay. So they have. You can look this up. They have a device or multiple devices, I believe, which are various types of plasma accelerators. One is called QSPA. So QSPA. And there are some papers on this. So basically, they generate the plasma and they somehow accelerate it to create huge short heat loads. So the pulse lengths vary, I believe, from somewhere to a millisecond to fractions of a millisecond to even a microsecond, I recall. So they are, let's say, much more representative of what a disruption would be. They have already there are papers that you can find for how that works with lithium in some kind of porous substrate, not the 3D printed one, unfortunately. And the lithium one seems to perform fairly well. So there, as far as I know, there is no damage as long as you make that substrate out of tungsten and not of anything else. Yeah, and now the question is, will that work with the 3D printed samples and will it work with liquid tin? And yeah, maybe I don't think everybody knows this, but tin and lithium melt at roughly the same temperature, right? At 180 degrees for lithium and 230 for tin. But tin does tend to evaporate much less easily. So that is why you can have some higher surface temperatures with tin, also in a reactor. But that is at the same time the reason why it might be not as resilient to disruptions as lithium, because you need a much higher temperature to evaporate sufficient tin. And maybe that temperature is in excess of the tungsten melting point. I don't know, but it's possible. Yeah. So we will see. I don't know if that answers your question.
Yeah, it does. Thank you.
Okay. Yeah.
Great, thanks. Then
You meant me, Thomas?
yes.
I didn't fully get the. Yeah, thank you. I have a question, Peter, which is related to very fast transient events like disruptions, where the replenishing of the layer will never be fast enough. I would think that given the thickness of the layer, you should then be able to calculate the maximum energy that you can spend before you've evaporated your complete layer.
Yes.
And what kind of numbers do you then get?
Yeah, excellent question. Okay, I would have to look it up. But so we did this indeed, and it's in a paper I published. You can look it up if you want. It's from 2017 or so, and we did exactly this. But for the numbers, and also I should say we looked it up for. We calculated for lithium, which is not tin. And the calculation is very dependent on how exactly you assume the evaporation rate to be dependent on temperature. So right there are of course equations, a Langmuir equation that describes evaporation, but then there's also redeposition and all kinds of processes in the plasma. So what is then the effective evaporation rate? You need to know this, and then how much energy does one particle dissipate in the plasma? Does one particle of lithium dissipate, I don't know, 500 or 5 electron volts, right? So, and that already shows you there are some order of magnitude errors here. But nevertheless, if you would have a lithium surface thickness of, let's say, 0.1 millimeter, so 10 to the minus 4 meters, 0.1 millimeter, I would say if the lithium radiates very effectively in these conditions, so let's say it dissipates about 500 electron volts per lithium particle, you can withstand a disruption of, let's say, this is 1, 2, 3, 400 megajoules per square meter. So that is about 200, let's say, 400, 800 gigawatt for a millisecond, right? So you can withstand astronomous amount of power if you evaporate enough. And indeed, it's limited by the surface thickness. Yeah.
If I understand your question correctly, this depends mostly on the radiative losses per evaporated atom rather than on the energy required for evaporation.
Yes. So the energy required for evaporation is about an order of 1 electron volt, right? Whereas you can calculate from collisional radiative modeling the cooling that happens in the plasma just because the particle heats up and gets ionized and then radiates. And then at some point radiation becomes a really big contribution above a certain electron temperature, and actually the main contribution. And so you can get definitely up to these orders of a few hundred EV for lithium and higher for tin. Yeah.
Okay, thank you.
Yes, thanks for the question.
I think I can also add on as a comment, Peter, that it depends a lot on what the redeposition rate is during this disruption, because you can have a, let's say, non-coronal behavior where you have a lot more radiation per particle because the lithium is ionized, radiates a little bit, but then returns to the surface, and this process repeats many times per second.
Yeah.
And this can be a force multiplier, let's say, for how much power is radiated by the lithium.
Yeah, definitely. And this is definitely an important point. So it influences, right, the amount of lithium available more or less, and how much temperature it takes to get it off the surface. But also, one more thing even is that during a disruption, there are of course electric currents also going through the wall, right? There is quite a probability of that, and they are going to exert huge forces on the liquid metal, and maybe they are pushing it out of the CPS, or let's say towards the plasma-facing surface, towards the plasma. And yeah, you can see that as a bad thing, right? Maybe it will then fly through the reactor chamber to somewhere you don't want, but also maybe it will locally increase the amount of available lithium. And actually, there is a student working on this right now as an intern. So yeah, this is a very interesting topic. Okay, but experiments will show. Yeah.
Then I think we have a couple more questions, so I would like to get to them. So first we have Jelle de Vries.
Yes, thank you, Peter. So I have more of a practical question. So you mentioned that your design for your wall will be about a meter tall. And I think that the current walls are quite a lot smaller, from my understanding, and that there is not that much space available in the most devices. So do you think that this could be a problem?
Yeah, good. Okay, yeah, good question. And but actually, to answer it is to understand more or less the design process. So the way the European demo design works is there's a central design team. They make sort of, let's call it a system architecture, and of course also on a concept level, but nevertheless it's an architecture, and they divide the space. So they say, Peter, you have to build the thing of 70 centimeters high. And I say, okay, and that's it. And they have, of course, their reasons for choosing this height. So they, for example, say, look, the strike point is going to be this wide. The control systems are going to be this accurate. So we need this margin around it. And then we add some safety margin. And they see then if that fits, like you said, if that fits with all the other systems. But of course, demo is quite big. The major radius is what, 8-9 meters. So this is big, but maybe not too big. Yeah.
Okay, thanks.
Does that answer your question?
Yeah, no, it's good. Thanks.
Yeah, it's a demand. Yeah.
Then I think we come to the last question, which is from Suleiman.
Hi, Peter. Thank you for the presentation. I am looking for an answer. Why does lithium work? So you give some clues about this in your presentation and in the answer section. So one of them was because it can suck hydrogen. So that means that you have to form lithium hydride, but we know that lithium hydride is not a very stable compound. I mean, there are other metals that can suck hydrogen more efficiently. Did you also quantify experimentally the physical reason why lithium works? So for instance, can you quantify formation of lithium hydride, or can you quantify other properties related to lithium? Let's say because lithium has a low cohesive energy, that means that it can separate into atomic form, so it can create new ions. So it can eject ions into your plasma. So for instance, can you look into this kind of issues? And the last issue maybe is the secondary electron emission. So when you have the bombardment from plasma, so you have high energy electrons that goes to metal, and then the metal electrons have been excited, can be released back to the plasma. So can you quantify this kind of effects in your experiments?
Okay, let me see if I get your question straight. When you say when the liquid metal works, when the lithium works, what do you mean exactly works for what? For the effective vapor shielding?
I mean, you presented like it's a good solution for the diverter.
Yes. Okay. Okay.
So,
yeah. Okay.
so
good. I think I
the
understand.
physical reasoning why it works?
Yeah. Okay. I think I should maybe nuance then my answer a bit. So I think lithium works great when it comes to power handling and probably some other things, but let me state the most important is that this tritium retention issue, because I mean we have done experiments, and also actually other PhDs in the group of Thomas have done extensive experiments with on the retention of tritium or deuterium, right? And I really think for the European demo, you should be extremely careful. So it would be much preferred to use liquid tin. Okay, then as to your question, why does it seem to work? Unfortunately, my experiments do not give much insight into this, I should say. So my experiments mainly show that it does work, and it shows to what extent it works, how much power you should be able or should expect to handle. But to really say what is the mechanism, right? What is the dominant, let's say, is there more recombination or is there more ionization, and what is the resulting balance between ions and neutrals, and in what charge state are they, and from what transition do we get the most radiation? My experiments I don't have results that show you this directly. You would need to really focus on the plasma physics, whereas I focus more on the power handling. That being said, you can do that. You can, of course, do that. There are plenty of good spectroscopic diagnostics on Magnum. So if you wanted, you could set up a study and dive into this in detail. And what I should also say is I believe modeling will give you a very good insight into this. So there have been students and there are PhDs that differ. For example, Ray Chandra, if you want to talk to him, for example, he is working right now on sort of SOL-PS type modeling. So Monte Carlo coupled with plasma fluid code to look into this into much greater detail for lithium. Tin is of course more complex, but you can do it. And of course you could benchmark. You can use my experiments to benchmark these codes, right? So you can say, look, the code says that we should expect this much power to be dissipated by a vapor shielding, and you can compare it to the experiment. And in fact, we also have experiments pretty recently that show you where evaporated lithium goes through, so we know something about transport. I know in the past, you should ask Thomas, there was a lot of work on secondary electron emission. Okay, but I have to disappoint you a bit. I cannot give you a detailed answer on this, I'm afraid. Yeah.
Okay, thanks.
Okay, unless I'm mistaken, I think you were able to answer. You answered everybody now, Peter. So I'd like to thank you again for a very nice talk. So let's thank Peter again.
Yes, thank you all for attending.
And thanks everybody for attending.
Give me this chance.
Yeah, don't forget to vote. Don't forget to vote for Peter for the New Scientist Award. So you can find it in the chat. And I think maybe it was also in the email for the invitation.
I will put it in the chat again. And yeah, thank you very much.